Swayam Prabha. Digital India. Educated India.
So, this is the spectrometer which was built for gas phase photoelectron spectroscopy in the Indian Institute of Science, Bangalore in 1980. In 1980, it was built here, and then a lot of spectra were recorded using this spectrometer. It still is there. It's almost 40 years old spectrometer. It is still there. Okay. So, that is the analyzer. You are talking about analyzer. The analyzer would look like something like this. This is a gold coated, the surface has to be absolutely smooth. There should not be even a speck also, the electrons will disappear. So, so this is a gold coated analyzer inside, and you know this picture? How many of you know this one? Tata. He is the one who founded Indian Institute of Science 100 years back. How many of you know Indian Institute of Science? So, he is the person who founded that, right? I did my PhD there, that is why I like him. I like that institute, is a very good institute. If you get a chance, please go and visit Indian Institute of Science once. Okay? Okay? Alright. So, we said UHV is important, ultra high vacuum is important for X-ray photoelectron spectroscopic analysis. The reason for that is you maintain this pressure of the order of 10 to the power minus 9 torr or even less than that. Actually, current spectrometers, they maintain up to 10 to the power minus 13 torr, 10 to the power minus 13 torr. It is not easy to get that kind of vacuum. That is a kind of vacuum. So, that is to remove the contamination. If, as I said, this is a surface sensitive technique. One has to maintain the surface clean for longer time, longer enough to complete your experiment. That would be, let us say, you wanted to finish your experiment in 40 minutes or 1 hour. So, the surface of the material that you are analyzing has to be clean, kept clean for at least for 1 hour. So, that is possible only if you go, if you reduce the pressure to of the order of 10 to the minus 9 to minus 10 torr. Okay. So, that will remove the, that will keep the surface clean, and also to, even if when you take some material and put it inside, you will see that it is clean, but atomically it may be dirty. Atomically it may be dirty. So, what people use they use this argon ion beam, 3 kilo electron argon ion beam, and then remove the layers, atomic layers, dirty layers, and get the surface, clean surface to record the spectrum, right. So, you have that argon ion beam to remove the contamination, right. X-ray technique would cause damage to the surface, but it is negligible. If you are using biological samples for analysis, one has to be careful and see whether X-ray is damaging the sample or not. Normal metals, oxides and normal solids is okay, but if you are using a biological sample for XPS analysis, you have to be very careful, see whether it is X-ray, whether the samples are stable for the X-rays that we are using. Okay, all right. Otherwise, generally damage is negligible. So, to create vacuum, you have to have something like oil. You have this rotary pumps. Rotary pumps you must have seen somewhere. You must. So, you probably will see in future. So, rotary pump will bring the pressure from 1 atmosphere, that is 760 torr, to 10 to the power minus 2 to minus 3 torr. It will reduce the pressure. Beyond that, if you want, you have to use these oil diffusion pumps, mercury diffusion pumps, turbomolecular pumps, ion getter pumps, titanium sublimation. There are all variety of pumps people use to reduce this pressure further from 10 to the power minus 2, minus 3 to 10 to the power minus 8, minus 9, minus 10 torr. Okay, these are the things. And then the pressure is measured using gauges, Pirani gauge, ionization gauge. There are certain gauges which are used to measure the pressure. This is the instrumental details. So, do not worry about that, but this can be done. Okay. So, this just to quickly give you from the kinetic theory of gases that we have learned already, kinetic theory of gases, if you see here, if you use, for example, the pressure is number of atoms is equal to 10 to the power of 6 into P monolayers. If pressure is equal to 1 torr, pressure is equal to minus 6 torrs, Ns is equal to 1. N is equal to number of surface layers, right. If you are maintaining that is actually that calculation can come from kinetic theory of gases, okay. So, if you maintain the pressure at 10 to the power minus 6 torr into 10 to the power of 6 gives you 1, N is equal to 1. So, N is nothing but the number of atoms or molecules in one monolayer. So, if you maintain a 10 to the power minus 6 torr for 1 second, you will get one layer of atoms or molecules contaminated on the surface. That means, if you will not be able to do your experiment at minus 6 torr, you will not be able to do, your surface will be clean up to 1 second. If you maintain this pressure at minus 6 torr. Now, minus 7 torr, minus 8, minus 9, minus 10 torr, that will increase to almost several hours. That is the reason why you need to use pressure of the order of minus 9 to minus 10 torr. Okay. So, that is basically some kind of a estimation using kinetic theory of gases. Okay. Now, coming to the surface, suppose you have a solid has layers, top layer atoms, second, third, fourth layers atoms are there. Now, if these are all the photons which are coming in the solid line, these arrows are all photons, these are all photons, they come, see some of the photons are ionizing the atoms on the surface layer. Oh, this is very sensitive, huh? It is too sensitive. So, these light atoms are surface layer, top layer of the atoms, and then if the electrons are coming, the photons are coming and ionizing the electrons, these are electrons which are coming out. So, these are all, when the top layer atoms are ionized, electrons are coming out without losing any energy. They are actually they give you the clean photoelectron spectrum. But then if the photons are going deep into the layers, that is 1 micron, and then these atoms get ionized, the electron which is coming out here, this electron has to pass through these layers. When it is passing through those layers, it is going to hit the charges around. So, that way it loses its energy, kinetic energy. That loses its kinetic energy. So, that will not give you, this will not give you clean spectrum, that will become a background. Suppose if it loses energy, kinetic energy, so it will not have the memory from where it is coming, because part of the energy is lost during its travel to the surface. Okay, all right. So, the same thing is given here. So, this is the X-ray photon, for example, it is going inside, these are the top layers, this escaping photoelectron, whereas this is going here, this is also photoelectron, but it is passing through, it is losing its energy here. So, the electrons coming from the deeper layers are not going to give you clean photoemission spectrum. They form background. On the background, you have a spectrum coming from the electrons coming from the top layer of atoms. That is why it is surface sensitive. Suppose if we have some kind of adsorbate layers or contamination, then these electrons will not come out. So, you will not be able to see the substrate spectrum. Okay, all right. Okay, so now that is a solid. Now, let us say now I have so I have a sample. The sample has core levels. These are all electrons. This is a core level. As you go up, you have the valence band, because these are valence electrons come together, form a band, where the core electrons are localized, the localized energies. Now what I will do, I use my HNU and then remove these electrons, these are electrons, I keep removing them. So I get a spectrum like this, exactly map of that. You see, this will give you a peak here, these two will give you peaks here, that will give you the band here. So you are exactly mapping the electronic structure of the solid. Okay. Somebody told you in your class, there are orbitals, there are s orbital, p orbital, d orbital, pi star orbital, right? How do you know what is the experiment that you can do to see whether those orbitals exist or not? What experiment is you can do? Photoelectron spectroscopy. This is experimental evidence that the orbitals are present, s orbital is round, p orbital is dumbbell shape, etc. Shapes are different, but there are orbitals are there, electrons sitting inside that. Have you gone into the atom and then went into the orbital and see there is electron there? Can you see an electron? But can you see the electron? Can you see atom? Can you see an atom? No. We are all breathing. What is going into our nose? Are you seeing it? You are not seeing it. But you are saying now, you are saying air is there. In that air, what molecules are there? How do you know? The oxygen is there in air. How do you know that? What experiment will you do to prove that oxygen is there in air?
Sir, we can have a candle.
Yes, okay. So people have done all that, right? There are indirect experiments which tells you that, so these are all there. So here orbitals are there, atomic orbitals are there, molecular orbitals are there. So the evidence comes from the photoelectron spectroscopy. So now this is how it is. Now if you see, for example, in this spectrum, in this binding energy diagram, there is a maximum that is occupied here. Up to this point, electrons are there. Beyond that, there are no electrons. There are energy levels here also, but then there are no electrons to occupy that, because number of electrons are limited. For example, you take one element, it has limited number of electrons, right? So I have got a number of electrons will be there, limited number of electrons. So there is a maximum level at which the electrons are filled. So that level is nothing but EF, Fermi energy. That is called Fermi energy, right? So if you wanted to see the binding energy, and then this is the kind of spectrum that you get. So this is taken as, EF is taken as 0. EF is taken as 0. That is a reference point from where you measure the binding energy as you go deep inside.
So for different metals you get different levels, but what if the sample was a compound instead of an element?
So there also, for each metal there is a EF, you can easily identify that. If it is a compound, for example, a organic complex, there is a reference point. The carbon 1s reference point, they take it, with respect to that they measure, right? That is, there is a reference point you have to define. Okay. Normally what happens is, in these compounds, for example, you take some complex and then record the spectrum, they refer the binding energy with respect to carbon 1s. Carbon 1 is, in any sample there will be some carbon will be there, adventitious carbon they call it. So that carbon will give you around 285 electron volt normally. So that is, they take it as a reference point, and with respect to that they define. Okay, all right. But in this case, if it is a metal, you can straight away say this EF is equal to 0. From there you measure the binding energy. As you go down, binding energy increases. You see here up to 1400 electron volt. This is 4p. The N is equal to 4. You don't need to go to N is equal to 3, 2, 1. That is not required. That is the N is equal to 4, 5. If you analyze, that will give you enough information about the elements present in the sample. Okay, all right. That is good enough. If you want to go to n is equal to 3, 2, then you have to use X-rays very high energy. You don't need that. You don't need that. Okay, all right. So now you see here this P, the intensities are different. Somebody was asking, these intensities depend on the ionization cross section. Ionization cross sections, right? So there is nothing but probability of absorbing photon by a particular electron sitting in a particular level. That is not same for all levels. Okay, that is not same for. That is the reason why you have different intensities here. Okay, all right. You got some idea of what it is. Now let's go to the real spectrum. This is an actual spectrum taken from a book, Practical Surface Analysis book. This is a spectrum of some, I think it is one of the transition metals. I don't remember this one, but one of the transition metals. Now here, you look at the spectrum here. So you start from 0 here. This is EF is equal to 0, right? Now here you have 4d electrons. That is the top electrons. That, right? So then 4d, 4p, 4s. This is the n is equal to 4 shell. You are getting peaks here because of the electrons ionized from 4 n is equal to 4 level. Then you come 3d. 3d level, there is a peak here. 3d electrons are ionized here. Then you have 3p. There are 3p peaks here, and there is 3s here. So you can see the electronic structure is nicely mapped there. Electronic structure of that particular element. I don't know what that element is, but one of the transition metal element. Electronic structure is nicely mapped. Notice that the energy here, the background is very low here. See, when it goes here, the background goes up. Again, the background goes up. This energy, this background is nothing but secondary electrons which have lost their kinetic energy when they are coming from the bulk. When they are coming from the bulk. So this MNN is nothing but Auger emission. I talked about Auger emission. Auger emission comes here. Auger emission comes here. MNN is nothing but KLMN shells in X-ray notation. So I didn't give you that, but that is this. Auger emissions are also part of X-ray spectroscopy. X-ray photoelectron spectrum will give you that also. Okay, all right. Now here, this is the binding energy is increasing. You know, this is 0. This is 0. The binding energy is increasing. EF, no, I said no here. See, EF 0, binding energy is increasing. So now here, the binding energy is increasing. This is EF is equal to 0, binding energy is increasing. Kinetic energy should decrease. Kinetic energy should decrease should increase in opposite way. Correct? Now HNU is equal to kinetic energy plus binding energy. So if kinetic energy, binding energy increases, kinetic energy should decrease. That is the next slide will tell you. Next slide. Okay, this is the spectrum. So kinetic binding energy is increasing, and then kinetic energy is increasing in opposite direction. That's correct. Kinetic energy plus binding energy is equal to photon energy, HNU. All right. Now you see here, this is another spectrum. I don't remember what this one is. Again here, EF is here. EF, this is a small valence band is there. Whenever you are using X-ray XPS, the valence band intensity is generally very low. Valence band intensity is very low. The cross section is very low. That's why you have a small valence band here. And then you have this 2s, 2p, and so on and so forth. This is the Auger, and this is 1s electron. I think this is the one of the oxygen atom. Oxygen or okay. So this is how it looks like. So again, kinetic energy is increasing. This in this direction. Binding energy is increasing in this direction, opposite direction. Okay. All right. Oh, what is happening? Oh, spectral interpretation. I have to say that. Okay, all right, all right. So that slide is not working for some reason. Okay, so now since this is there is a background here. Notice that there is a background here. Oops, there is a background is increasing, background increasing. What normally people do is they remove this background. These are secondary electrons. They are not of much use for us, because this is the spectrum these are the peaks which are important, which are overlapped, superimposed on the background, right? So people try to remove that background. Okay, so they use different types of background removal methods. Don't worry about that, but there are different methods to remove the background. Okay, now this one shows a copper sample recorded. This spectrum copper sample, copper 1000, this is 1000-volt scan recorded using aluminum K alpha. So here these are the Auger signals. Oh, this is very sensitive. Now this is the again same copper sample, which is spectrum is recorded using magnesium K alpha 1253.6. This is again the same Auger, 3 peaks. Notice that this Auger is coming around 600 to this region. The same region Auger is coming here also. Sorry, this is 800, not 600. Can you see this? Are you able to see this? This is 800. This is 800. Auger peak is coming at the same value, but you see this this peak. This is actually the one of the XPS peak. This is coming around 600 and around 700 here, and here it is coming around 300. The same peak is coming at different kinetic energy. This kinetic energy is different, whereas this kinetic energy 800 is same. Why is that? Auger electron kinetic energy will not depend on the ionization energy or the energy of the aluminum K alpha or photon energy. It does not depend on the photon energy. Whereas kinetic energy of the photoelectron depends on the photon energy. That is why the Auger electron kinetic energy remains same in irrespective of whether I use aluminum K alpha or magnesium K alpha. Okay, that is a test whether that particular spectrum, whether this particular peak, these peaks are Auger or photoelectron peaks. This is a test. One can do that very easily. But nowadays it is very easy to identify them, because once you start working in this area, just by looking at it immediately you will say this is Auger, this is XPS. Is that clear or not? Auger electron kinetic energy will not depend on the photon energy that you are using, whereas photoelectron kinetic energy depends on the photon energy that you are using. Okay, all right. Now the question is, why doublet? 2 peaks are there. Somebody asked. So these 4D electrons, normally what we expect is a single peak. But you are seeing a doublet, 2 peaks are there. That is because the phenomenon called spin orbit splitting. It's a phenomenon called spin orbit splitting. How many of you know that? Have you heard of that? Spin orbit splitting. What happens here is, this is too much here. These guys have to. This is. I can't use this now. This mathematics department has to correct this one. Huh? I can't explain this to these guys. Okay, all right. Okay, I'll do one thing. Okay, or otherwise I will use this. You have the pen or something here? Please call them, because I have put some lot of yeah, they would know how to correct it. Okay, in the meantime, suppose I have orbital. In the orbital, how many electrons can you put? Maximum 2 electrons with the same spin opposite. So net spin is 0, right? So that orbital will be, let us say, is sitting in a particular particular L value. What your spin is S value, right? You have L value, right? Suppose say out of these 2 electrons, I remove 1 electron. So the remaining electron will have half spin, right? Now this orbital will have L value. Once you remove that electron, this L orbital angular momentum will mix with this spin angular momentum. They both mix and give you another quantum number. That is J value. So J is equal to L plus minus S. It can be plus half or minus half. So that will give you 2 different final states. Initial state is spin is 0. Final state will have two final states. So one final state will have one peak, other final state will give you another peak. That is why you get split peaks. So that happens for p, d and f orbitals. Whereas s orbital, L is equal to 0, right? So L plus S, L minus S has no meaning. Only one value will be there, right? L is equal to 0. So either you will have only half. Any 1 electron you remove, you have J value is going to only is going to be half. So you have only one peak in case of S.
Could you please repeat the parts for the P, D and F?
Can you please correct this? See, I have some arrows put in my slide, but it is showing like this. Is it possible to correct it? Okay. So some question was there. What is that?
Please repeat. Could you please repeat what
For example, you have, let us say, p orbital, px, py, pz. Take px orbital, you have 2 electrons there, right? Or py or pz. So you have all two electrons. So remove one of those electrons. So the remaining electron will have s value half, right? And then p, what is the L value for p? 1. So 1 plus half. Or remove the other electron. One is spin down, spin up. Remove the other electron. Minus half. So L minus half plus L plus half. So you will have 2. So L is equal to 1, 1 plus half or 1 minus half. 1 plus half is equal to 3 by 2, 1 minus half is equal to half. So you will have P 3 by 2 peak, P half peak. 2 peaks will come. 2 final states. So that is how you get. But then these
I will upload your files to one of our application. From there I will open it.
okay.
This is CCM open source or IIT only. I will upload those files. From here I will open you and show you.
Okay.
Because we don't have Microsoft Office in this machine.
Oh.
Microsoft Office.
Oh, I see.
It's open office.
Oh.
So I will upload it here and show you.
But later on you have to delete that.
I will delete it.
Acha, so that why don't you install that here?
Microsoft is very installed. It is commercial. It is very installed.
No, you should install it because these kind of things. The third one. Second one. That one.
Only this file you want to upload. No other file you want.
That is sufficient. Will it work now? Oh, correct. This clarity is better.
Ah, sir. That is open.
Here it. Now it is okay. It is working. Okay. Thank you. So, so let's come back to this spectral interpretation again. That so these are the peaks. So there is a doublet here. 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 But where is this? There is no doublet in S electron. So this is these are the basically the these are the background electrons. These are all background photoelectrons which have lost their energy while traveling to the surface. Whereas these peaks are the original photoelectron peaks without energy loss. So these are the spectra which we have to look for. This we don't need to worry about. This gets they subtract it. Okay? Yeah.
Sir, for d orbitals, we also saw like a similar difference in these peaks. Is it because of the difference in like the orbital energy, like the T2G and EG configuration? Is it caused by
T2G EG is basically because of the splitting of d orbital under the influence of the pointed charges. That is a different one. That's a different.
It's because of this J is equal to L.
Yeah, I'll just show you that. Now here, now this look at this one. That's what I was saying. In the initial state is there are 2 electrons. And you take any orbital, you take 2 electrons are there. Initial state H nu is there. You can remove either this electron or that electron. So remaining electron is only 1 electron. This is the final state without spin orbit interaction. You have only one state. Now with the but then you have a different L value here. L plus S n minus L will give you 2 different states. You can see that one here. This is the orbital angular momentum, spin angular momentum. So the orbital angular momentum will have some value. Spin angular momentum can be either plus half or minus half. So the total angular momentum in this final state is going to be either L plus S or L minus S. Right, S is equal to plus half or minus half. So you get p orbital will have these 2. Accordingly, you see that L plus S, that is 1 plus half will give you 3/2 here, and 1 minus half will give you half here. But it has a degeneracy. Degeneracy means it has the same energy, right? So the degeneracy can be calculated by using 2j plus 1. J is a quantum number that you are calculating here. 2j plus 1, 2 into 3/2 plus 1, 2 into half plus 1. So that will give you 4 and 2, right. So the P 3/2 is more intense, twice the intense than that of the P half, right. So that is the spectrum. You can see the spectrum here. You should get P 3/2 intense peak. Other one will be half of that that intensity. The energy difference is nothing but your spin orbit splitting energy. That depends on the again L value. So we will not worry about that, but there is a difference, right. Okay. So this is the actual spectrum. This is what I have just given as a pictorial this one, but this is the actual spectrum of p electrons. For example, silicon 2p. P orbital can be anything. P orbital can be 2p, 3p, so on and so forth in any element. The behavior of this p orbital is going to be same. The 3/2 half we should get, irrespective of whatever element you are talking about. Whatever p orbital it is, it can be 2p or 3p or 4p or so on and so forth. Okay. So this is a silicon 2p. You can see this is the intense one, 3/2. This is half into half of that intensity. Okay. If you take the area of this, so p 3/2 and p half, area of that if you calculate and then see it will be approximately 2. Okay. So that is how it is. So this goes on for other orbitals as well. For example, if you see, for example, X-ray photon ejects from electron of 2p level of silicon surface, spin angular momentum of the remaining 2p electron occupies remaining electron 2p level couples with its orbital angular momentum to form total angular momentum J. There are two possible values, half and 3 by 2. So, that is what it is. The degeneracy is given by 2j plus 1. So, now if you calculate the ratio of the 2p peaks that you are seeing, so intensity, if you see, intensity is equal to 2p 3 by 2 by intensity of 2p half, that is experimentally measured. Whereas, this one theoretically 2 into 3 by 2, 2 into 1 by half plus 1 and plus 1. This is a theoretical one. So, that should give you 2, this should also give you 2. Theoretically, what you predicted is 2p 3 by 2 and 2p half intensity ratio should be 2. Theoretically also you will get 2. Okay, that is P. Now, let us do it for d orbital, you do it and tell me. For d value, d orbital, I have ionized a d electron, removed one electron from d orbital, and what kind of splitting that you will get? What are the levels, final states that you get for d orbital? Sorry? 5 by 2 and 3 by 2. 5 by 2 and 3 by 2. Similarly, f orbital. So, p, d, f orbital, all orbitals will have a splitting, spin orbital splitting, 2 peaks, doublets you will get. So, that is what is given here. See, the p orbital we have already talked about, d orbital will give you 5 by 2 and 3 by 2, f orbital will give you 7 by 2 and 5 by 2. Area ratios are also there. From j value, you can calculate the area values. So, this remains the same irrespective of where the element is present, whether the element is present in a material or in a complex or in a compound or whatever you take, this is ratio is going to be same. Okay, all right. Theoretical calculation should match with the experimental observation that we are making in the in the spectrum. Okay, all right. So, now you understand why you have doublets there. All right. All of you understood that? Okay, good. So, points to remember. So, for P, D, F peaks, doublet peaks are observed because of the spin orbit splitting. And then for S electron, no doublet peak because L is equal to 0. L plus S, L minus L is 0. So, there is no point in talking about doublet there. Separation is due to spin orbit splitting. Why they are splitting, right? And the values of spin orbit splitting of a core level, an element in the different compounds are nearly same. The spin orbit splitting difference will be same with respect of where the element is present. I mean, which the compound can be, it can be a complex or it can be an oxide, it can be a sulfide, it can be anything. So, the level with highest J value has the lowest energy, that is the Hund's rule. That is the Hund's rule that you all know that. Okay, all right. So, these are some of the points that whatever till now we have talked about. Now, this is the electronic state effects, spin orbit splitting. I am just giving you examples of copper 2p. For example, you take 2p. Now, copper 2p, copper has a 1000 volt scan. So, suppose you want to take 2p, there is a region you have to take. Or d electrons, copper 3d electrons will have a particular region, right. So, copper 2p comes between 965 to 925. That is the binding energy region where copper 2p comes. Now, we have 3 by 2 and half, these are the two peaks, and that difference in spin orbit splitting is 9.8 electron volt. That 9.8 electron volt is going to be same whether copper is in copper oxide or copper sulfate or copper chloride, whatever. That difference is going to be same, 19.8 is same. Okay, and intensity ratio is also going to be same irrespective of where the copper is present. Okay, so the orbital P, L is equal to 1, S equal plus minus half. So, you have S is equal L plus S n minus 1 will be 3 by 2 and half. Okay, that we have already seen that. Similarly, d orbital will have 5 by 2 and 3 by 2. These are the peaks, and then the spin orbit splitting energy is only 6.0. It's not same for P, D and F. It varies. Okay, all right. So it depends on the L value, depends on the L value. Similarly, f orbital will have 5 by 2 and 7 by 2. This is 5 by 2, that is 7 by 2. The energy difference is 3.65 electron volt. Spin orbit splitting. The energy between the two states, two final states, is going to be 3.65 electron volts. And peak area is 3:4. That's what we have calculated theoretically also, right? Theoretically, we calculated that. You calculate that, see whether 3,4 is correct or not. J value is there, no? J value 5 by 2, 7 by 2, 2J plus 1. 2J plus 1. 4 by 3. 3:4 or 4:3. It depends on which one you are referring to. You can do it all around also. Okay, all right. Okay. Now, next important thing is there is something called chemical shift here. The element which is sitting in a particular compound, if its chemical environment is different, the binding energy will change. The binding energy will change. That is a very important concept in photoelectron spectroscopy. Look at this one here. This is a compound. This is a ethyl trifluoroacetate. This is acetate actually, but trifluoroacetate, ethyl trifluoroacetate. You have this 4 carbons are there. So you can record carbon 1s spectrum, for example. Carbon 1s spectrum you can record. If you record carbon 1s spectrum, all our carbons, you should get a single peak, carbon 1s peak, right? Yes or no? All are carbons. So you should get carbon 1s, a single carbon 1s peak, but then the spectrum shows 4 peaks are there. The same compound, different carbons, 4 carbons, 4 peaks are there. What is the difference? What is the, how do you understand this? Now the carbon which is sitting surrounded by 3 fluorines will have delta positive charge, because the fluorine attracts electrons, right? Fluorine is inductive, negative inductive effect. You have studied the inductive effect in organic chemistry? Negative inductive effect. Fluorine attracts electron charge from the carbon. So the delta positive charge is more on carbon, which is surrounded by 3 fluorine atoms. Similarly, carbon CO, this one will have this delta positive is more than this one, and this delta positive is more than this one, this delta positive is more than that one. So they have delta positive charges because of the environment, chemical environment is different for all 4 carbon atoms. As a result, the binding energies are not going to be same, but the binding energies are going to be different. That's why you get 4 peaks. This peak obviously will have higher binding energy or lower binding energy, this one. This one is corresponds to this carbon. Is a higher binding energy or lower binding energy? Higher binding energy, because if fluorine withdraws electrons from carbon, so delta positive charge is more. The delta positive is more, then it is difficult to remove electron, 1s electron. So binding energy is going to be higher. Binding energy is going to be higher. So you have this higher binding energy. See, this is the binding energy scale, that is the kinetic energy scale. The binding energy is high here. It is almost 294 or something here. And then next one is 291 or 285, so on and so forth. This is called chemical shift. This is called chemical shift. This is a very important thing. The moment you see this chemical shift, then immediately should come to your mind. Suppose I have oxidation state, different metal oxides, metals for example can have different oxidation states. So binding energies will be different. So based on the binding energy, I should be able to find out the oxidation state of the element present in the compound, right? So that is the advantage of measuring the chemical shift. Look at this spectrum. This is silicon 0, oxidation state is 0, and here SiO2 oxidation state is +4. So, the binding energy here, this is binding energy is 99.15 for the silicon, valency is the oxygen state is 0, whereas in this case oxygen state is +4, there is a shift in binding energy by about 4 electron volts. So, if you record a spectrum and you see the binding energy is 103.4, you can immediately infer that silicon is present in +4 state. Silicon is present in +4 state. Okay, all right. So, that's one of the, so when atom loses valence charge 0 to +4, the binding energy increases. When atom gains valence electrons 0 oxygen, this should be negative, I think. The binding energy decreases. Suppose electrons are given away, binding energy increases. Electrons are taken, then binding energy decreases because charge is more. So, the binding energy will decrease. Binding energy will, because the same nuclear charge has to be distributed to all the electrons present there. Okay. This is another experiment. The titanium 0, that is a titanium sample, a metallic sample, titanium. It's recorded, 2p spectrum is recorded. You can see this is the binary, this is the 2p 3/2 peak. The same 2p 3/2 peak is shifted by about 4 electron volt from 5 electron volt in when it is titanium 4 plus. TiO2 and Ti. TiO2 will have higher binding energy, it is shifted by about 5 electron volt, right. So, that is the another interesting thing that chemical shift is going to be helpful to us to find out the nature of metal ion present in the oxidation state of the element present in the sample. And remember here, see this is titanium 0, oxygen is also recorded. This same spectrum you can record oxygen also. There is no peak here. Why? The back, there is just a, there is no peak there.
Because
There is no oxygen. There is no oxygen, right? So, there is no oxygen here. Whereas the TiO2, oxygen is there. See, very strong oxygen peak is also there. So, you can record titanium 2p as the oxygen 1s and then check. Yes, there is oxygen, strong oxygen peak, and there is a peak shift in 2p by about 5 electron volt. That means this my sample is TiO2. That is your conclusion or inference. Okay, that is how qualitatively you can do all that. Now look at this, and you tell me now. This is I just want you to tell me. This is sulfate ion. This is the thiosulfate ion. If I record the spectrum of sulfur 2p, for example, sulfur 2p, how many peaks I will get here and here? How many I will get? This sulfur is surrounded by 4 oxygens, whereas this sulfur is surrounded by 3 oxygen and 1 sulfur, right? Whereas this sulfur is surrounded by nothing except this group. So, this sulfur chemical environment is different, this sulfur chemical environment is different, this sulfur chemical environment is different. So, you will get single peak here, you will get 2 peaks here because 2 sulfur peaks you will get, right. So, sulfate will give you a single peak, sulfur 2p, whereas thiosulfate will give you 2 sulfur peaks because 2 sulfurs are there in 2 different chemical environments. Okay. So, that is how one can actually draw some nice conclusions from that. Now, look at this one. This is the spectrum of sodium. What is this? Nitrate, azide. What is that compound? Sodium azide. Sodium azide. Right, this N3 minus will have this kind of a structure. You see here, it gives 2p. If you record the photoelectron spectrum of azide, that is you are recording nitrogen 1s spectrum. Remember here, nitrogen 1s you are recording. Nitrogen 1s is between around 410 to 390. That is the region nitrogen 1s comes. If you record that, nitrogen 1s shows two peaks with two different intensities. How do you explain that? Obviously, this is a structure. So, there are two n minus ion, there is one n plus here, say at the center. So, 2 n minus will have lower binding energy or higher binding energy? Lower binding energy. You see the lower binding energy, and it is, the intensity is twice than this, that because I have 2 n minus are there, intensity is twice. Whereas n plus higher binding energy and its intensity is only half because there is only one n plus. The other two are 2 n pluses are there. So, beautiful qualitative information. This is a structure. Now, that is confirmed. That is confirmed now. Okay. So, these are this kind of thing. This is because of the chemical shift. Chemical shift. Okay. All right. Now, this one is another interesting thing. This is an experiment I have taken from a journal called Langmuir. Now, here what is interesting here is that there are 3 peaks, 1, 2, 3, 1, 2, 3. Don't worry, in this case the sample is exposed to air, that is why the intensity is increased. But then you see here, suppose such a spectrum is given to you, all are 1s, boron 1s, carbon 1s, nitrogen 1s, oxygen 1s. Is that interpretation correct? Somebody gives you that, asks you to interpret that. Find out, these are all 1s peaks of boron, nitrogen, carbon and oxygen. You have to identify that way. Is it correct or not? Is it correctly identified? This peak of carbon 1s, etc. Is it correctly identified? Nitrogen should have? You have to see the atomic number and then nuclear charge. How many protons are there? What is the atomic number of boron, carbon, nitrogen and oxygen? Which one will have higher nuclear charge, oxygen or nitrogen? So, higher the nuclear charge, higher the binding energy. So, oxygen 1s, this oxygen 1s electron, oxygen 1s electron in oxygen is experiencing higher binding energy compared to this one, and compared to this is higher than carbon 1s, this is higher than boron 1s. Nuclear charge keeps on increasing, boron, nitrogen, carbon, nitrogen and oxygen. Okay, is that understood, all of you? That is because this is a sample contamination is less, whereas the other sample was taken from air, so it collected some carbon is increasing and oxygen is increasing. You see this carbon and oxygen. If you expose the sample to air, it is collecting some dirt, some oxygen means then maybe some water absorbed on that, and carbon, some carbon is getting absorbed on that. That's what I am saying is very sensitive, very sensitive. See, it is freshly mechanically exfoliated HBN sample with XPS analysis chamber, this one. Whereas this HBN is directly transferred to analysis chamber, aged HBN. Aged means, outside. So, it collects a lot of oxygen and carbon, right. So, now the intensity is different. That is why it is very important that you keep the sample clean. This is a clean sample, freshly mechanically exfoliated sample, fresh sample. Okay, all right. This one, this is the XPS sample of moon dust. It is actually dust was taken from moon. Somebody has brought it and then they wanted to know, analyze that. So, what do you understand from this now? First point is moon has all these elements. What are there on earth also? Right? Moon has oxygen, carbon, silicon, aluminum, magnesium, all those elements are there on moon also. But you must be looking for, gold there. Right? If there is a gold, everybody will go to moon. Right? So, and then of course, the different orbitals are also there here. So, one of the main conclusion is that it has all the elements which can be identified, using photoelectron spectra. Okay, all right. I think I will skip this. This is the one which is surface sensitivity. Here, this experiment was done long back. This is a clean gold foil. Clean gold foil will have 4f electrons. These are 4f electrons, 4d electrons, and 4p electrons. Now, initially, some 70 years, 80 years back, people recorded this spectrum in the form of a photograph, the film. There were no electronic systems where you can record a peak nicely and all that. Those days they used to expose the electrons coming to a photographic film and develop it, and they see the two lines. These are the two lines which we are seeing today as two peaks. Initially, when people did that experiment, at that time these electronic systems were not there. So, they were recording everything, a photographic film they are putting and exposing it, and then developing it, and see there are two lines there. What are those two lines? People were struggling to interpret them. But today we have come to a stage where what those two lines are, what is the intensity differences, etc. we are able to explain all that. Now, the same sample is taken and then after fingerprint, some dirty fingers, put a finger on that and record the spectrum. It says there is no gold. See, there is no gold. Are you seeing that? There is no gold there. It says only the carbon is there, some silicon is there, some oxygen is there. So, a dirty finger put a fingerprint on that, and it says there is no gold. That means it is a very, 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 very surface sensitive method. One has to be very careful, clean the sample and record the spectrum. Otherwise, what you record, what is present there will be different. You have to remove all the contamination on the surface and then record the spectrum carefully. Okay, all right. Okay. So, that is all. And then UPS, I do not know how much time I have, but in the UPS spectrum, that is about solid surfaces recording the spectra. Suppose I have a gas phase molecule, for example, hydrogen. I will give you one example and then end this one. Hydrogen molecule, if I have, hydrogen molecule will have sigma and sigma star orbital. Sigma orbital will have 2 electrons. So, this is how it is, right? The 2 electrons. Now, I remove this electron, photoionize this electron. The same experiment what I did, I do it here in the gas phase system. I remove one of these electrons. See, this is a molecular orbital. Remember, this is not atomic orbital. This is a molecular orbital which we are talking about. This is what we have learned, molecular orbital theory, right? All of you have learned that or not yet? Right? So, how do I know that such orbitals are existing or not?
We count the bond order.
Sorry?
We count the bond order.
Bond order?
Bond order of this MO diagram. Like the number of bonding orbitals minus number of antibody orbitals. So we can know the
bond orders. Yeah, that is okay. That is what your theory tells you. Have you actually seen that into the molecule and the bond order is 1 or 2 or 3? Theoretically, that is what is explained nicely, right? Experimentally, experimental evidence comes from the photoelectron spectroscopy. Now, here what happens is, I remove one of these electrons. This electron I remove this. If I remove this electron, now this will have a potential energy diagram like this. You are familiar with this, right? Potential energy diagram. It has a potential energy diagram, right? Now, this is a bond, this is the equilibrium bond length, this one. If I remove this electron, this will have vibrational levels. The molecule vibrates. It has vibrational levels. They are quantized. They are all quantized. Right? Now, if I remove the electron from this, then what will happen to the bond order? Bond length also decreases or increases? Bond order decreases. Bond length? No. You have one electron is there still. Bond order is half. Bond length, what happens? Bond length will increase. Bond length will increase. Now that means this is the equilibrium bond length here. Now when it is ionized, one electron is removed. This is shifting to higher. Interatomic distance is increasing. Bond length is increasing here. You see that? And then these are all vibration levels. So this electron, this transition, when you remove this electron, the molecule will go from here to here, this vibrational level. So that is the most intense line that you will get. Of course, you will get the other side also. There are levels here. So that will give you a vibrational progression like this. This is the actual spectrum recorded for helium-1, the ultraviolet photoelectron spectrum of hydrogen. It will give you all these peaks. This is different from solid. Gas phase molecules tend to give you this kind of vibrational progressions. This is for hydrogen, nitrogen, oxygen, so on and so forth will give you similar spectra. Okay. This is gas phase photoelectron spectra. It is possible to record photoelectron spectrum of liquids also. Okay. I am not going to touch that now. Okay. This is little, you may not understand this immediately now, but this is also an important thing. So summary is that HNU is equal to kinetic energy plus binding energy. Laboratory photons are used here. Of course, one can use synchrotron radiation. Surface sensitive technique, sensitivity is 20 to 50 angstroms, not 50, this is about 100 angstroms. Spin orbit coupling gives you doublet peaks in PDF orbitals. Intensity depends on the degeneracy. Chemical shift in XPS depends on the chemical environment. Higher binding energy satellites appear due to shake up. This I have not touched it. I have not touched that. That is another one. Gas phase photoelectron spectra show vibrational fine structures. Example, hydrogen I have talked about. Oxygen, nitrogen, oxygen also will have a similar thing. Okay. So that is the summary of that. Okay. This topic is over. How much time I have? Over? Huh? What time is it? 5? Oh. Only one topic I covered. One more topic? Okay, all right. So, I also have to go. 5:40, yeah. Oh, I have to go. I have also another thing. So, there is another topic which I wanted to talk to you about, scanning tunneling microscopy to see electron density, to map electron density of atoms. That means you can almost see an atom. That will take another 1 hour. So, I may not have time now. Maybe some other class if there is a time, if there is another day. Okay. So, have you understood something? Is it okay? Is it got some idea? Right. So, if you have a piece of gold, the gold that we wear is a pure gold? Alloy of what? How do you know the copper is there in that? You take that gold, put it in the spectrum, it will tell you copper is there. Suppose if in the shop, if they say, no, sir, there is no copper, these days people are actually adding iridium in that. No, sir, nothing is added. So you bring that one, take a spectrum here, and it will tell you iridium is there, copper is there, gold is there, or any other element is there. They can't cheat you. So as a scientist, you should be able to catch them.
So what if they gold plate the iridium?
Sorry?
What if they gold plate the iridium? Then you won't be able to get it.
Gold plate iridium. You scrape it. You can actually, there is something called etching procedure. I have not given in the, there is something called in the spectrometer, there is etching process. It removes layers and layers and it can go deep. So you can actually go and map, inside what is there. So you remove the layers. That technique is there, right? So you have to be scientifically thinking, right? If something is given, we should be able to answer scientifically, concretely to the question that is posed to us, whether it is science, engineering, medicine, whatever it is. We should have we should cultivate scientific thinking. Remember that. Whatever profession you practice, but you should cultivate the organized scientific thinking to find answers. Okay, that will take you. And the last point I want to tell you is, don't become slaves to AI tools. Don't become slaves to AI tools. The tools should be your slaves. You should use them, not they should use you. The moment you become slave to the tools, they will dictate you what to do. So you will lose your brain. Your brain is the ultimate. You should decide what to use, how to use, and the tool should be in your hand. Remember that. Okay? Don't depend too much on everything. Depend on your own tool. What is your own tool? Sharpen this tool. This is important. Okay? All the best to you. Yeah.